I knew that Brandon would say far nicer things about me than I would say about myself, so my first slide's blank. My name is Dan. I work here. That's about all you need to know about me. My name's on the meetup if you want more. There's Google. What's that? Here as in Olsen, yes. Physically here. So this talk is about types, and I think if you read the description on the meetup, the motivation for this is kind of that all of a sudden the JavaScript community cares about types again. And we're going to get to some of those details about TypeScript and Flow and ASM toward the end of the talk. But I am incapable of thinking about anything without, I guess, going all the way back and talking about CPU architecture, because I guess everything starts there. So really this talk is about three things. First, it's going to be just about computers. Second, it's going to be about thought, because I don't know how you could get more pretentious than just talking about CPU architecture type talk, so might as well just talk about the nature of thought. And then finally, because this is a JavaScript meetup, in fact, we are going to talk about JavaScript in sort of the last third. So first off, computers. How do they work? I told you, James, this was actually a slide in the deck. So we're really just going to talk about two things about computers. Obviously, there's a bunch of stuff in your computer, but when you think about like the design of how our system actually processes stuff, there's two things we're going to care about for the purposes of this. The first is the CPU, and the second is memory. I said RAM here, but there's a bunch of different kinds of memory. And the reason we care about this is literally everything that you run in your computer, every piece of code that executes, at its very base does three things. First off, the CPU is going to take a string of bits out of some address on memory. Second, it's going to feed that string of bits into some actual circuit on the CPU, like actual electricity, that's going to perform some logic on those bits, and then it's going to dump it back into some other memory address, some other string of zeros and ones in memory. So literally everything we execute on our computers does that at some level. So this is not a CPU, but if we think of a really, really simple integrated circuit, this has 4 operators in it, and they're all ands. And all this is, okay, the laser pointer's not going to work. All this is if you apply electricity to those 2 wires, you're going to get electricity on the 3rd wire that comes out of it. But if you only apply electricity to one of the 2 wires, or 0 of them, then you're not going to get electricity on the 3rd. So this is essentially an implementation of the logic operator AND in an integrated circuit. And so if we think that ultimately what assembly language is it's one keyword in the language for every circuit that's built into the processor that can execute one step of pulling something out of RAM, doing one operation on it, and then putting it back into RAM. If this were a full CPU, this language would have one keyword. It would have AND. It has 4 of them, but that can only do one thing. It can AND things. So obviously our CPUs today are much more complicated, but ultimately they're based on doing millions of times a second, billions of times a second. They're based on taking some data out of an area of RAM, doing a single operation that's actually a circuit on it, and putting it back into RAM. So if we compare that stupid simple chip to an x86 processor, the x86 instruction set, so the number of different circuits it has on it that can do different operations, there's weird ways of counting based on aliases for things and operations on different areas of memory that actually do the same thing or are kind of the same circuit. But the best guess is sort of that there are about 2,000 different actual circuits in your processor that can do operations on RAM. And if you write assembly, you are essentially writing a list of those operations and a list of where it takes things from RAM and puts it back in. And generally, the operations that are in the CPUs that we have today are divided into kind of 3 different components. There are certain circuits that actually do operations on integers. So an add operation, you could say, take the string of bits at this place in memory, the string of bits in this place in memory, and write the addition of those into this place in memory. That's a single instruction cycle for a CPU. Similar math operations are increment, decrement, there's multiplication, kind of the things you'd expect there. The second thing we can do is we can move data around. So we can just say, take something out of this place in RAM, put it in this place in RAM. There's also some facilitation for stuff like stacks of things in memory, so kind of organizing structures of RAM. And then as a second group of still arithmetic operators, we have the same functions that we have for integers, like add, increment, subtract, etc., except on floating point numbers, so on numbers that have decimal places and then a variable number of things behind them. And this was actually kind of a revolution in the very early days of computers. Originally, you had to sort of emulate floating point numbers on top of integers, but I guess relatively early on, they sort of had separate instruction sets for operating on floating point numbers. But that at its base is basically all your computer can do, is arithmetic, move data, and arithmetic on different kinds of numbers. So if we think about this in terms of types, it looks like we have at least two data types here. It looks like we have integers and floats. But actually, the only actual data types that your processor understands or actually knows about the type of are byte, word, double word, quad word, and sometimes there's another one called 10 bytes, which is just 10 bytes. And literally all this is that a byte is 8 bits, a word is 2 bytes, a double word is 4 bytes, and a quad word is bytes, yeah. So, and quad word is sort of new because 8 bytes is 64 bits. So if you have an operation on 64 bits of data, that's something that only a 64-bit processor can do in one operation. And so when everybody switched from 32-bit apps to 64-bit apps, 5 years ago or so, that involved adding a bunch of instructions to the CPU that could operate on twice as much data at a time. And we talked before about integers, but really, when you store an integer in memory and you address it in assembly, the memory and the processor doesn't understand anything about it other than that an integer takes up or a 32-bit integer takes up a double word, and a 64-bit integer takes up a quad word. So you could have anything in that memory address. Maybe it's part of a string, maybe it's a random string of bits. You could run an add operation on it, and it would interpret it as an integer. It doesn't care what's there. It's just data on RAM. It's bytes of data, and the only thing it cares about is the size of the number of bytes that the operation is going to work on. If you think about, based on that, the only thing we get is 1 byte, 2 bytes, 4 bytes, or 8 bytes. If you start to think about how you might do string operations, so we no longer have integers, we no longer have operations in the actual CPU that can do things like concatenate two strings. But ultimately, if we want to concatenate hello and world, what we probably have is we have hello sitting in 5 bytes at addresses 1, 2, 3, 4, and 5, because there are 5 letters there, and each takes up a byte. And then we probably have world sitting at some other memory address. We'll say it's 10. So that's taking up bytes 10, 11, 12, 13, and 14. But remember, we can only operate on one of these at a time. So if we wanted to write something like this in assembly, we'd first have to create an integer somewhere. So that takes up a double word somewhere. We need that because we need to first count how much memory we're going to need for the concatenated string that goes together. So then we're going to iterate over each string, every letter, and count them, and use that integer to store that count value. And which is complicated by the fact that in assembly you don't have any loops. The only flow control you have is essentially goto. It's a little more complicated than that. So we're going to calculate the lengths of them. Then we need to look at our memory table to find a place that has at least 10 bytes or 10 bits in a 10 bytes in a row available, so that we know we can put that concatenated string somewhere. And then we iterate over each character at a time again and use a move command to move it to that new memory address where we know we have 10 available and we can put the two next to each other. Obviously, this is not an ideal way to program. So with no types or with only functions that operate on numbers, life is hard. This is the scenario in programming until about 1953. And in 1953, or actually he said this later, but in 1953, this guy John Backus came up with this great idea to write a program that wrote programs for him. And like any good programmer, I think this is true. Every tool we build comes out of being lazy. We don't want to do stuff anymore, so we automate it. So I think it's great that, well, this is obviously most of the work we do was funded by the Department of Defense at some point. He was writing programs to compute missile trajectories, and he thought it was hard, so instead of doing that, he wrote a program to generate programs so that he had to write less code to do that. And from that, we get the first higher-level programming language, which is called Fortran, which it stands for something like for translation, I don't know, but basically it's just specifically designed to work with numbers and includes some constructs like some really basic loops. The first version doesn't even have if-then. It just has like a thing that says, it's like go to if this is true is the only sort of decision construct you have.
Formula translation.
What's that?
Formula translation.
I don't have a clue, and that was probably the incorrect. It's.
Wikipedia.
All right. Well, you can explain after the talk then.
I'm just explaining that here.
Okay. So Fortran it's a small language. It doesn't do much, but it's a lot better than writing assembly. And it has 32 statements in the language. And one of those statements is punch. And if you think back to the fact that we were just worried about string handling, there's a very important reason that this language doesn't care about strings yet. And that's that the entire input-output interface for computers at the time looked like this. They were bits punched into punch cards. I've actually never seen one of these. I would love to, but if anybody in the room was around during the era. But really, this is still sort of internal representation of bits and encoding numbers. And when this is your input, worrying about text strings is not really an issue. And worrying about abstract data types is not really an issue because you can't really abstract much when you've only got that many bytes to deal with and you're punching them out by hand on a punch card. Some guy on the internet did a much more thorough survey than I did of if the word type was ever mentioned in the Fortran manual. And so here's kind of the only place they come close is to say that any expression can either be fixed or floating point, but it can't be both. So this doesn't really improve on the assembly version of expressions are designed to operate on them, but as far as judging types as some kind of object in their own right, we're not there yet. And yeah, there's a couple more things about that there. But importantly, this does introduce a program to write programs, right? And so this is the first time we get a compiler, which is a program that takes something you write in a language that's not assembly and then applies a lot of the like complication that it abstracts over and then spits out an assembly that'll run on a machine. Interestingly, as an aside, this was the first time that anybody thought of the idea that if you had two different computers, you might be able to run the same code on both of them, because before compilers, if your processor were any different, you had to completely rewrite the program. So the first idea we ever had of portability also. So this kind of remains the situation of things until about 1978 or the mid-1970s. And over the last 25 years, two really important things happened in the development of computers. The first one was teletype machines, which, if you're not familiar with this, what this was, it's like a typewriter where you type on the typewriter a row of input, and then the computer types back to you the answer to that input. And this seems archaic, but the important thing here is now the interaction mode we're having with computers is text, not with like bits punched into a punch card. And then in the next decade, in the 1960s, we finally get CRT monitors. And I'm fascinated about this because when they first came out with CRT monitors, they actually, so if you look back at like the ENIAC, there will be a bunch of flashing lights. And when they first came out with a CRT monitor, they were like, great, now we can just have one square that has a bunch of squares that represent the flashing lights. It wasn't until after teletypes and then like another decade goes by that they say, oh, we could just display the text on the screen. That would be a great idea. So we get tech, we get displays, and the most interesting one on here is the one on the bottom right in 1978, the VT100. And this is interesting to me because the terminal protocol that literally every single one of you in this room continues to use in a console window to this day was written for that computer in 1978 and hasn't changed since. So in 1978 or in the 1970s, as we move toward these more text-based interfaces, the language that emerges is the first one that many of you have probably written some of, and that's C. Yes. And C is a pretty low-level abstraction over the way the processor and assembly think about memory. So for example, here is a stupid little C program, and all this does is it sets a variable, an integer to 1, and then it increments it and it prints it. But the important thing here is that that operation of incrementing the integer directly maps onto a single assembly language instruction. So this is going to compile down to just the add call in assembly. It's the least we can do to sort of add an abstraction over it. C also introduces strings, but it sort of doesn't. So all a string is in C is they added a data type called character, C-H-A-R, and a character is actually equivalent to an integer. It takes up a fixed number of bytes and really just represents a number written on disk, but you can use ASCII to map that to text. And all it does to represent strings is it's an array of integers. So really, this is just sort of syntactic sugar for saying we're going to declare in memory 5 integers, or 5 characters, and then we're going to set them to HELLO, and there's actually a 6th one that indicates it terminates. But this works, and I don't think, yeah. So we have basic strings in C. But kind of similar to the issues that we thought about when we thought about how we might manipulate strings using just assembly, we still have the same memory declaration problem. So the first line, we're declaring one string that's going to find 5 or 6 bytes in memory and put HELLO terminate in there. The second one is going to find 6 bytes in memory and put WRLD terminate in there. And then C has this string library, string.h, which provides a bunch of functions. Even though this data type has no functionality except being an array of characters, they build abstractions on doing things with those. So there's the strcat function that concatenates 2 strings. And let's just run this quick. And immediately it crashes. And this is going to be the first super interesting thing about thinking about when we start talking about static versus dynamic types. Notice I didn't split this out very well, but in this command line, everything before the and is compiling it. So we're running the C compiler, and then we're just saying we get a binary out and then just execute the binary on the command line. Notice the place it crashes is on the execution, not the compile. And if we look at what this is doing, so this is in a place in memory, this is in another place in memory, and we don't have to allocate that manually or anything because these are literals in the program. So the compiler is smart enough to say, oh, there's 5 characters between quotation marks. That means we need to allocate 5 characters of memory. But now, the output of this is going to be 10 characters of memory. And we could be passing, these are literals, but we could really be passing sort of arbitrary strings into concatenate. So we can't know at compile time that we need to allocate 10 characters of memory when you call concatenate, because it could be any number depending on the number you're passing in. So ultimately, what we're trying to do here, what this does is it appends 2 to 1. So we're trying to write WORLD into a string that doesn't have enough space for it. And C doesn't care. It'll let you do that, but it'll crash. So the way you fix this is by manually allocating enough memory. So you've got to calculate the length of one string, then the other, then make a new string called both strings, and then you copy the first string into the second string, and then you concatenate the second string onto the first string. And you don't need to understand the allocation mechanics or anything, but realize we didn't have to loop over the letters one by one, but we didn't really improve a lot on the mechanics of how you have to sort of move strings around in RAM in order to manage them. So just before we move on from C, just a couple other asides about data types. So we talked about arrays of characters. C also has arrays of other things. So that function at the top should really probably be called print character, because then it's trying to print a character. But that takes a character array. And then down here, we're going to make an array of integers. And then we're going to pass the integer array into the character array. And this is smart enough to do a type check on those arrays, and so you can't do that. Although, interestingly, it's only a compiler warning, not an error. So it says you shouldn't do this, but maybe you wanted to anyway, so And you can silence the error if you just add an explicit cast to a character pointer, and then it works. I didn't put the output there. Then it works fine, but it also either crashes or just doesn't do what you expect it to because the wrong kind of data ends up being there. So it has static type checking, but it's not very safe in forcing you to actually have statically checked types. We also get from C the beginning of what starts to look like user-defined types or objects. So we can define a struct, which is just like a really, really rudimentary object. It's just basically a list of other data types that are kind of kept together in memory. And then we can call typedef on that and call it mystruct. And then down here, we can have a new variable that's just mystruct. So we've made a new type there. And this works like you'd expect kind of an object to work. We can set the string property to that. We can print it out. And it prints out string and then show the output. We also have some type checking on, or more specifically, you can't dynamically add those. So in JavaScript, if you have an object and you just try to add a new property to it with a dot that never existed before, that's fine. But that'll give you a compiler error in C. And for two reasons. One, you could think of this as some like static type checker saying you probably didn't mean to do that. But really, it's all about memory again, because this struct knows that it's big enough to hold one integer and then the literal number of characters we assign there. But nothing's ever accounted for having contiguous in memory to that struct another property, and so there'd just be no place to put it. It's a function of not letting you use memory you shouldn't that is really why this stuff has to happen. Okay, so we start to get an idea from this of what we mean when we talk about static types. First off, we have a compiler. That compiler is doing some kind of compile time checks for static types. And additionally, you can't change the structure of types at runtime. So if you have a compound type that has some other members to it, you can't change that compound type and then add another sort of member to it at runtime. But importantly, it's not necessarily safe, because there's a lot of sort of memory safeguards here that the type system just sort of emerges as a necessary property of the language, but is not necessarily giving you constraints that say your program is correct and it's not going to do bad things, which is often what we think of when we think of type systems. All right, section 2, thought, increasing the pretension by 1. So in the 4th century before Common Era, there was this guy named Aristotle, and he is credited with inventing logic, and he probably didn't, but we like to rewrite the history with the West ahead. There's a school of Indian logic that was probably first and some other stuff. But he started to think about the way we reason about things. And the way that he formalized that with this idea of syllogisms. And so the classic example of an Aristotelian syllogism is, all men are mortal, Socrates is a man, therefore Socrates is mortal. And there's a bunch of different forms of this argument. You can have some statements in there, you can have no statements in there. But the thing that Aristotle sort of realized about reason that nobody else did before is that it's the form of the argument that matters, not the actual objects you're reasoning about. So with that, Aristotle essentially invents variables, because you can say for anything in the world, all A are B, X is an A, therefore X is a B. This kind of gets dropped for the next, like, 1,700 years. No, wait, 2,100 years. Probably because Christianity. But the sort of, and a lot of the reasoning that went on during that time was they started to really care about sort of what this meant ontologically, and like, if you could reason about objects that doesn't exist, what does God think about that? But we finally pick it back up again in the 19th century. And there's various work that goes on between those. And what they realized in the 19th century is that there's actually two different types of things here. So A and B are essentially categories, but then X is a thing that belongs to that category. And so they formalize this. We're not going to get too deep into the symbology here, but they formalize this by saying, we can say, okay, X is a variable that represents a thing, and we can say, for any X, that's what the upside down A means, and I switched from man to human here because they're the same letter and also sexism. So h of X, if X is a human, the arrow just means if the left, then the right. So if X is a human, then X is mortal. And the first sort of formalism of this form of splitting this idea of sort of categories of things from variables of things was formalized by Gottlob Frege initially, who's probably the only name in here you don't hear very often. So the next thing that happened is this guy named Boole, who you have heard of because we named Booleans after him, realized that one way we can think of H and M here is that they're sets. So we talk about sets in math, the set of all the natural numbers, and there's a lot of sort of mathematical proofs based around sets. And he realized there's a correspondence here between the fact that H is a property that holds true of X means also that H is the set of all human beings, and M is the set of all mortals, and that this statement is equivalent to saying the set of all human beings is a subset of the set of all mortals. And that symbol in the middle means is a subset of. So there was this correspondence between formal logic and set theory for a long time, and they listed a bunch of axioms about how you would reason in this way. And this works for about 20 years until you get to this guy Bertrand Russell. And I'm not going to explain everything on here, but the basic axiom of set theory is that for anything that is a member of a set, which is the X, E, Y thing, so if X is a member of the set Y, that's true if and only if there's some property that's true about all X's, which means for any set that you define, you can say there's some characteristic property that defines why a thing is a member of a set. And you can really quickly from that, if you define that property and do a little wizardry about X is the set of all things that are not in themselves, you can basically get a bug in this reasoning system. You can define a contradiction where you can say, okay, true is false. And this gets mathy because you're talking about these sort of abstract concepts about sets. But ultimately, this completely upsets all of logic for a significant amount of time. Bertrand Russell spends the rest of his life trying to solve this problem and finally gets to an answer that is called, now you see where we're going, type theory. So here is this guy Kurt Gödel, who did a lot of work about formalizing the completeness of sort of mathematical systems. And you don't really need to read all of this, but there's two things that are important in this. Instead of sets, which exist kind of independently, they reformalize this into an idea of types, where the difference are that types have to have a relationship between them, and specifically are often hierarchical. And that's essentially it, but there's a couple other things in this quote that I think are super important for this. We didn't get from the Fortran manual any of the common language that we use to talk about this stuff today, but all of a sudden I forget the year on this, but early 1900s, all of a sudden in this statement we get types, we get objects, even though they're talking about objects of thought, but computer objects are abstract objects, they just didn't have computers at the time. And we get classes somewhere, I think. So the language that we sort of use to talk about types is starting to get developed in this sort of math logic realm. So the next sort of touch point on this, and this is probably the part of the story you might know, is that in 1936, actually in 1920s, there was this problem posed by Hilbert, who was a mathematician. I can't pronounce it. If anybody knows German, go for it. This was supposed to be one of the unsolvable problems in mathematics. And it essentially is stated, design an algorithm that can arbitrarily prove whether or not a statement of logic is provable. So if I give you a big statement of logic and I want to know whether it's possible to develop a proof for that statement of logic, The problem was, is it possible to have an algorithm that I can give that statement to, and it can either tell you, yes, it is possible to prove this, or no, it is not possible to prove this. And it was long thought that this was impossible, but in 1936, two guys proved it in different papers at exactly the same time. The first one you probably almost certainly know of was Alan Turing, and this was based on building a machine. He didn't actually build it, but was based on designing a model of a machine to actually attempt to execute it and then proving that that machine would never stop. So if you've heard of the halting problem, the previous problem essentially reduces to the halting problem. But more interesting for this discussion is there was this other guy, Alonzo Church, this ends up being called the Church-Turing thesis, solves the same problem using exactly the type theory that was formalized by Bertrand Russell and Frege previously, or not Frege, Gödel. And he does this by sort of doing this adaptation of it called the lambda calculus, which is where we get anonymous functions called lambdas today in programming. But what's interesting about this to me is Alan Turing did this in a very practical way by building a machine, or theorizing about building a machine, and Alonzo Church took a formal theory of logic and sort of worked backwards into a language that you could use for this. So we have sort of a practical approach and a theoretical approach, and they kind of end up in the same place. And I think this divide maps on to kind of what we've been talking about. So when we talked about C, really the reason we had types was because we have this practical problem in assembly language, which is reasoning about abstract things, or not even reasoning, programming about abstract things like strings is difficult. So really we're using types to construct more complex things to solve a real-world problem. And so there's sort of a language lineage under that. C is there, C++ is there, Java's arguably there. And then you can start from this sort of theory of logic idea. And this is the opposite. This is, we had this theory of reasoning that was contradictory because it was too permissive. So we're going to use types as a way to restrict the kinds of things you're able to say in that system in order to make it more provable and correct. And there's sort of a language lineage that comes from this side, including Lisp, ML, and Haskell more recently. And yeah. So to sort of help prove that point about kind of the two ways to approach this problem, we're not going to talk about Lisp much, but briefly, right around the same time C was being developed, in fact, I think Lisp predates C a few years, this language called Lisp was also under development. And there's a lot of differences between C and Lisp, but I think the biggest conceptual difference is that in C, you're building the minimum number of abstractions in order to make it easier to write code that's as close to machine code as you possibly can. In Lisp, you do exactly the opposite. You say, let's make sure that none of our variables, that nothing we write in Lisp, let's make sure that has no relationship to machine code so that we're not tied to these sort of memory problems or any of those things. And let's just abstract that all. And then on top of that, we can think about a type theory for our own language that doesn't have to be constrained by the type theory of the machine or the actual types in the machine. And so this is, you're probably getting this, but this means Lisp is sort of the first dynamic language, or it can be the first dynamic language. And the other reason that Lisp is sort of known as the first dynamic language is it introduces this idea that there's no difference between the code and the data that the code operates on. So the sort of only data type in Lisp is called a list, and so that is a literal representation of a list at the top. Forgive the curly quotes because PowerPoint. And that second line is a bit of Lisp code that basically says add up 1, 2, 3, and 4. And notice that essentially the syntax of an actual piece of Lisp code and a literal list in Lisp is identical, more or less. And this is because all the code that's going to execute in your Lisp program is actually stored as a Lisp data structure. And this lets you do the first sort of dynamic things, which for one thing is we get an operator like a function call that lets us call a function by its name, which might be stored in a variable rather than having that have to be a static definition in the system. There are ways to sort of rewrite parts of the language at compile time, and it is still compiled. And so from that, we can sort of start to get a definition of dynamic types. The first thing that's important is that they rely on memory being 100% hidden from you. You can't have any constraint about mapping to the way assembly actually thinks about things, because you need to be able to manipulate things dynamically in a way that wouldn't be supported if you were directly dealing with memory. And the second is that we have structures and behavior that can change at runtime. And I think these principles are more important than just like a variable can be any type, because that doesn't mean anything. So this is sort of what I think is a decent understanding of a dynamic language or of a dynamic type system. One more programming language before JavaScript. This one's really quick, but we talked about constrictive types being from sort of type theory in logic. But Lisp is sort of the opposite of that. It's very loose with typing. It's a dynamic language. And it's, again, that opportunity that we're not sort of inheriting the type issues of the machine. Now you're able to build this super dynamic language. But now that you've completely abstracted that away, the other thing is you can take the type system you want and impose that, because it can be an internally consistent system on its own that doesn't necessarily map to the machine. And so ML is a language that essentially took type theory as it was codified by the mathematicians, put it on top of something like a Lisp, and basically just made the type theory executable. So now an ML program with some affordances for input and output, you can run mathematical proofs against it that say that this program is correctly typed. And so this is, again, this distinction that in this case we're talking about mathematical types from type theory versus constructive types that we build just because we need abstractions over machine code. This is a good spot for an interlude quick about strong versus weak types. So everything you've ever read about this is probably wrong, because nobody actually knows the difference between these things. And oftentimes when you hear about weak types, you'll say, well, if the language lets you do something like 1 plus foo, it doesn't enforce. It's about the context you use them in. If it treats the variable as what you think it wants, what it thinks you want to do with it when you use it, that's weak types. But there's a version of this where 1 plus foo might just be syntactic sugar for calling a two-string method on 1, and then that's totally fine in any type system. But in any case, we can basically say that JavaScript types are really weak because there's really no language where they could introduce a concept of like sort of equal to, which is what double equals is in JavaScript, and have that be accurate and not call that weak. So by most definitions, we'll say JavaScript is pretty weak. I think the only time you can actually say something is strongly typed is if you can mathematically prove that a program is sound based on its type system. And there are definitely scales to that, but I like that definition because, yeah, it's the only one that's accurate. All right, finally, JavaScript. So we've been talking about 3 things in the JavaScript world recently that have to do with types. Mostly people are probably familiar with TypeScript, but there's another thing that's happened in the last few years called ASM. And then there's another sort of competitor to TypeScript, or maybe with slightly different goals, called Flow. And when we've talked about what we want out of adding types to JavaScript, there's sort of 4 things that come up as far as I'm aware. The first one is execution speed, and this is really only concerned with ASM, so we'll cover that one pretty quickly. The second one is compile time validation. So like a static type checker, we want to be able to run something that before our program runs to give it information about whether the types are correct or not. The third is static analysis. So it's really hard to run like a security scanner against JavaScript because it just doesn't know, because you can modify things at runtime, it doesn't really know what data will be passed where. And the fourth is for code completion, essentially, and refactoring tools or tooling, which I care less about, but we'll talk about it briefly. So let's quickly, based on those sort of concepts we talked about, let's score JavaScript. So the first thing that we know is it doesn't do static type checking. So we can have a function that's supposed to be a function of a number that multiplies that number by 2, and then we can pass the string foo to that function, and it'll give us an actual number back, and that number is not a number. But we don't even get an error at runtime, but we definitely don't get an error at anything like compile time. What's that? No. And we talked about this a second ago, but I can't come up with any definition of weak typing by which JavaScript is not weak, so we'll just go with the fact that it is, since it's meaningless. It definitely allows dynamic modification of objects, so if you have some kind of object defined, you can add stuff to it later. There's no sort of template for objects. Even in ES6, if you have a class that's really just sugar over, you can still create an instance of that class and add stuff to it. And we can also, kind of like Lisp, we can modify the runtime behavior based on user input. So if we have some user input and we define a variable called fun for function, then we can have that function be different things based on the value of that user input. So there's no way you could possibly statically validate this because we don't know which of those two functions is actually going to get called based on some user input. And even one of them is expecting a string and one of them is expecting a number, but again, don't know. And then it clearly, I think we kind of knew this at this point because we're pretty high level and abstracted, but it clearly doesn't have types that correspond to assembly integers. We kind of know that JavaScript only has one number type and that they're all floating points, so at least we know we only have floats, and we're definitely not doing atomic integer operations. So the first of these three things that we're basically going to skip over, but ASM exists to solve only that last problem. So they wanted to figure out how to make, as we're sort of compiling languages into JavaScript, how they could make a version of it that could run faster. And all this does, it has more of these annotations, but the little binary OR with 0 after each variable is essentially an annotation that says that those variables are integers. And what's interesting about this is, if those weren't there, and you just ran this with normal JavaScript, this would, again, we have a whole virtual machine under it. We've got a whole bunch of abstractions to make sure that our types behave like we want them to, not like the machine does. What this does is bypasses all those, where this add1 to x method will actually execute in a single CPU instruction. So the just-in-time compiler can look at this and can say, this is an atomic operation that we actually know how to execute this on the CPU, and it's only for a speed increase. But ASM is not actually designed to write. It's designed for other things to compile into, and it's also just a subset of JavaScript, so it actually removes a lot of other features. But that's interesting when we think about the getting data to the processor in the form it wants. They're actually doing that in part of JavaScript. So the next one that we're going to talk about briefly is TypeScript. And so TypeScript is designed for a couple things. One is just to add some static type validation to the language. So here's a function that says say hi, and we're passing in a variable called name, and the addition for TypeScript is that colon string in the arguments to that function. And so this is actually going to validate that argument is a string. And TypeScript, so we talked about static compilers. TypeScript actually adds a compile step to JavaScript. So you write TypeScript, you run the TypeScript compiler against it, it does its compiler checks, and if it passes, you get JavaScript out. But in this case, it's going to say that we're trying to pass a 20 to a method that only takes a string, and that's not allowed. So without even running this program, it can just look at it and say, there's a bug. What's up?
Isn't the number 20 actually a string though?
It's not. It can weak types, so it can be coerced to a string, right? I could add plus empty string to the end of it, and then it would be a string. But in this case, it's actually a number. The other thing it adds is, so static type checking, we covered that. The next thing it adds is this concept called interfaces. It has classes also, but this covers most of what we want to say about them. So in this case, we're defining this interface called a person, and all we're saying is that that has two properties, first name, last name, and that they're both strings. And then we're going to make an object, me, that has one property called first name, and that's my name. And then we'll write a function called say hi to person, and this says there's going to be a variable called the person, which is of type person. And notice we never, if you're familiar with other object-oriented languages, usually you would have something that says this implements this interface. But this actually checks them based on templates. So it knows that we're calling say hi to person with the object me. It's then going to look at the object me and say, does it contain all the properties that the interface had? And it doesn't, so it's going to automatically say that object does not conform to the interface with a less readable error message than that. The other interesting thing that it does is if I have an object and then I try to, so I have first name and last name on my object, and then after the fact I try to add a middle name property to the object, it's going to error and not let me add a property that wasn't in the original object definition. So that kind of satisfies that second object's modifiable at runtime. The interesting thing about this, though, is this has nothing to do with the interface. So if instead of doing that, we just, in the object definition, add a middle name property to it, then it's actually fine. This will compile and run fine, because the interface is only checking that it has the properties that it needs to have. It's actually just, it won't let you add properties to any object after it's originally instantiated. So here's an interesting experiment. So we talked about that last case about runtime modification of programs. In this case, we're going to pretend this is a Node program, and that declare at the top is just a TypeScript thing that's going to say, don't complain that there's a global variable called process in Node. So we're going to get an argument from the command line. So process.argv is the command line arguments to Node. And then we're going to kind of do that thing we did on that page, that first page of examples I showed, where we're going to check the value of that argument, and if that argument is equal to the value string, so if you type in string on the command line, then we're going to define a function that has a TypeScript annotation that says this function takes a string. Otherwise, if it's anything other than string, we're going to define a function where there's a TypeScript annotation that says that function accepts a number. And then after all that, after we've set that function at the bottom, we're going to call function and pass a number to it. So this is correct if the argument that I've passed to the program is not string, because then function will be a function that takes a number. But it will be incorrect if the argument to the program I've given is string, because then function will be a function that takes, or I had that backwards. You get the idea. So let's run the TypeScript compiler against that. Oh, I guess there are no errors shown. So the interesting thing about this is TypeScript doesn't find an error here. And this is interesting proof that the sort of dynamic nature of JavaScript that allows you to modify code at runtime sort of provides limits on what type annotations can actually guarantee for you. Because you're always going to be able to bypass them with this sort of dynamic behavior because, again, of the nature of it as a dynamic language. So switching quickly from, okay, we've kind of seen TypeScript lets you add type annotations, and switching quickly from that to Flow, which is similar to TypeScript, except has slightly different goals. And the goals of Flow are, without adding any annotations at all, we're going to do as much analysis as we possibly can to see if there are type errors in your program. And so this, you can see that this has a type error because we're trying to get a length property and we are passing a literal number in. So without running this program, we can just look at this and see that there's some point where we know we're trying to pass a 1 into a function that'll eventually try to calculate the length property of that, and it's not going to work. And sure enough, if we run the flow type checker against this, it'll say, you essentially, without running your code, you get a stack trace that says, this is going to try to pass a property to this that does not have a length property on it, or a variable to this that does not have a length property on it that it's going to try to access. So let's try the same thing with Flow, and I kind of skipped over this, but Flow does that, but then Flow also has the same type annotations that TypeScript does, so you can then give it more information about what to check but it will try to check stuff without it. So if we look at the same example in Flow that we just looked at TypeScript, same thing, we're going to get the process arguments. We're going to check if that argument's a string. If so, we're going to declare a function that takes a string argument. If not, we're going to declare a function that takes a number argument, and then we're going to call that function with I did a string and not a number this time. And if you scan this with Flow, it errors, whereas TypeScript didn't. And I didn't show both examples, but if you call this with string, you get this saying incompatible with number, and it prints out that line. If you call it with a number, it'll say incompatible with that string, or incompatible with string, and print out the string function line is the error. So TypeScript is giving up more quickly when you try to do sort of dynamic programming stuff to bypass the type system in JavaScript. And what's the last thing in here? Oh, now where this is interesting, well, it's interesting for a lot of reasons, but one thing is there might be times where you know the program is correct anyway. So if the only thing we add is a conditional at the end that says we're only going to call the function if we know it's the version of it that's going to accept a string. This will never error with a bug. It's also a pretty contrived example. But Flow will still give the same error on this, right? So there are times where you might know you've written a correct program, but where Flow's going to say, through static analysis, we found a possible code path where a type might be incorrect. The last thing that I think is really interesting is that both TypeScript and Flow will give an error on this piece of code that says 0 is not compatible with false, and you can't compare them with equals. But neither of them will give an error on this piece of code, and since really if is checking that something is truthy, this is equivalent to if 0 equals true. So they sort of fix the weak typing problem, but they don't fix this case, which I just find interesting. I don't think it's all that bad. So here's kind of what we've learned based on what we've seen from JavaScript and what we sort of know about types. The first is that these are still dynamic languages. You can do things like rewrite code at runtime and sort of call functions based on user input that are going to bypass a lot of sort of type annotations. And two, static analysis will always be imperfect. So sometimes we might know that something is correct, but the way the analyzer works is not going to catch it as incorrect, or vice versa. And I don't really care about IntelliSense, but if somebody's really passionate about using Visual Studio Code to hit tab and get the properties of their interface, you can talk about it in 2 slides. So then thinking back to our sort of constructive versus restrictive idea of types, the way that I think is useful for this is that there seem to be very different sort of philosophical goals between Flow and TypeScript. TypeScript is really designed to give you the expressiveness of a type system and to sort of let you build components in a sort of strongly typed way. And the really specific reason they do this is particularly like Microsoft and the Angular guys really like sort of the IDE tools that allows you to use around something. But Flow, I think, is designed to be more of a restrictive type system. Here we're trying to do something that's going to do everything it possibly can to validate the mathematical correctness of your program without running it. And we've shown that it can't be perfect. You can't write proofs that a lot of your JavaScript programs are incorrect because of their dynamic nature. But Flow is essentially going to get you as close to that point as it can. And so I think the question here, running Flow against your code doesn't really add any overhead because you don't have to add any annotations to try to get value out of it. But as we think about what kind of a language JavaScript is the overhead of rethinking about how we do architectural design in JavaScript into a more statically typed way. Is it worth the sort of half-assed safety guarantees we get from TypeScript and Flow? That's all I have.